I begin, I want to note that this is not a programming tutorial. This is not to teach you Java. We're not going to be doing any coding here. This presentation is to teach you guys the essence of what PID is and how PID relates to all the subsystems on the robot. Because all the subsystems, more or less, use PID to control the inputs and outputs into a subsystem. More generally, how a robot moves. And in the past years, only the programmers really had deep understanding of PID. But with this presentation, I hope everyone can come away with a greater understanding of what PID does and how it applies to different subsystems. All right, so let's get started. And Carson, feel free to chime in. And also everyone else, if you guys have a question and I explain something and something doesn't make sense, please raise your hand and feel free to cut in because this presentation is recorded, and so future members who might have similar questions to yours would benefit from you asking the question and me answering them. All right. Let's define a very key term, error. What is error? You didn't do anything wrong. It is the difference between where you're supposed to be, your goal, and where you actually are. So here Wally is at his location, but his goal is that red X right there. The distance between there is 5 meters. Thus, Wally's error is 5 meters. Let's also define what open loop and closed loop is. So say you have a motor and you want it to turn. Your goal is to tell it to turn at a velocity of 5 meters per second, okay? Open loop, ignore this side for now, this is closed loop. Open loop, go something like this. Hey motor, go turn at 5 meters per second. And I just walk away. The motor is now turning at, is it 5 meters per second? It might be a little weak and trying to reach 5 meters per second. It might be a little under in reality, or it might be a little too strong and turning at 5.5 meters per second. I don't know, because I just walked away and I just left it there. I didn't care. Open loop is something like that. It tells the motor to reach a velocity, turn at 5 meters per second. But it doesn't correct for any error. And as a reminder, error is the difference of where you're supposed to be, which is 5 meters per second, and where you actually are, aka the current velocity of the motor. So the motor might undershoot the speed. Undershooting meaning you set a speed of 5 meters per second, but it can't reach that. It's under. The motor might undershoot that speed, but open loop doesn't care. It might overshoot the speed, and it also doesn't care. That's why it's called set and forget, because you set the speed and you forget about it. You don't correct for any inconsistencies or error in the motor output. Closed loop, on the other hand, sorry, before I continue, this is, on the left side here, is kind of the diagram of what open loop looks like. Your plant is another word for subsystem, right? Plant is maybe not even subsystem. Plant is just what are you trying to control. In this case, it's just a singular motor. So your plant is the motor. You give it an input of 5 meters per second. It provides an output velocity. But at this point, you don't really care. And that's what open loop is. Now closed loop, you'll see the difference here. Closed loop is, hey, motor, turn at 5 meters per second, but I'm going to watch you closely. I'm going to watch you closely to see if you're actually reaching 5 meters per second. It keeps closed loop control, keeps track of error and closely monitors the error. So if the motor is feeling a little weak and undershooting the speed, I'm going to tell the motor to amp it up, put some more effort in, because it needs to compensate for the lack of speed. And if it's overshooting a speed, then I'm going to tell it to tone it down a bit, lower the speed, to put less power Now, naturally, because I'm monitoring the motor speed, it is more accurate than open loop control. Thus, it also introduces complexity. You can see the complexity here in this diagram on the right side, where this is the starting point right here. You provide the motor a set point. A set point is another word for goal. My goal is to have the motor turn at 5 meters per second. A controller is essentially the eyes watching the motor. This controller is the guy that is monitoring your plant, which is right here. And so your set point is 5 meters per second. Your controller is like, hey, plant, okay, the motor, turn at 5 meters per second, but I'm watching you. And the plant, the motor, will output whatever velocity it can, if it's under or over. Whatever it's under or over, this output will come back as a feedback signal. Feedback, like you're receiving feedback from a teacher. You get responses back from the motor, and it goes back into this loop. And that's why it's called a closed loop, because this loop is literally closed, like it goes infinitely. While open loop, there is no loop, right? And so whatever the feedback is, if the motor reports that it's undershooting its velocity, the controller will say, hey, amp it up a bit and put more power into the plant. If it's overshooting, it will tell it to lower the power. That's open loop versus closed loop. Any questions?
Where do we have closed loop on the robot? Do we have any open loop?
Yeah, so on the robot, anytime there's PID control, that's closed loop. Anything that has the PID or feed forward, that's closed loop. Open loop is the equivalent of percent output. On the robot, I don't believe there is. If there is one place, it is the swerve drive.
We have used it a little bit for the swerve drive.
Yeah.
We did just like percent output of the joystick.
Right.
And then converted that directly to the motor voltage.
Right. So for swerve drive driving, the benefit of open loop is that it responds quicker because you don't have a whole feedback loop right here. It responds quicker because the motor, you don't have to wait for the controller to process the error and do the calculations and everything. Thus, that's why I put the swerve drive on open loop temporarily, where percent output means a motor turn at 75% output speed, and then the motor may undershoot or overshoot, but I don't care. Good enough. Okay, let's talk about more terms. Feed forward versus feedback. Okay? So feed forward is essentially a prediction algorithm. Feed forward measures some constants and some constraints of your system, and basically with these feed forward constants, it will tell you some information on how the system acts in real life. Some examples of feed forward constants are static friction, the force of gravity, the resistance to inertia, the resistance to acceleration, and stuff like that. And you'll see in a little bit when I go into more depth about feed forward. It acts as a prediction algorithm because even though systems you can theoretically calculate how a system should work, in real life, things don't always go perfectly. And thus, these feed forward constants are really important information to telling you if you want the motor to turn at 5 meters per second. With feed forward, it will try to predict how much voltage you need to input into the motor to reach that velocity of 5 meters per second. Feed forward will essentially feed forward essentially embodies what you know about the motor. And if you give the feed forward an input of the goal, the set point that you want to reach, like 5 meters per second, feed forward will output you a voltage, the voltage to apply to the motor, because it does some math inside, because this feed forward knows a little bit about your robot. So that's why I say it's a prediction algorithm, because you tell it what set point it wants to reach, or what you want it to reach, and it will run its algorithm and try to predict how much voltage is needed. And that's based on like some theoretical calculations. Things don't always go perfectly. Now, this is, now if you just had feed forward, where you, as I said, feed forward, you give it an input of the set point that you want, like 5 meters per second, and it will output a voltage. If you just had feed forward, this would be the equivalent of open loop control, if you only have feed forward right here. Now, that explanation was a little confusing. I know, I'm sorry about that. I will go into more detail in future slides. Feedback, the difference is that feedback is a correction algorithm. Feedback will correct for any error that comes after feed forward. So again, things don't always go 100% accurately. Feed forward can try to predict the necessary voltage to reach the set point that you ask it to reach. But things don't always go perfectly. So feedback will correct for any error in that feed forward algorithm. And so this right here, what I highlighted, the feedback signal, this part, this feedback signal loop is what makes it closed loop. Again, that was a little confusing. Sorry about that. Does anyone have any questions? I will try to answer. Okay. Yeah. So feed forward here. Let me reiterate feed forward and feedback in simpler terms. Feed forward, you give it a goal you want to reach. I want to turn at 5 meters per second. And feed forward will try to predict, hey, I know that this motor is a little, needs a little lubricant, it doesn't turn as effectively, so I need to supply some more power to it. And so I'm going to amp the voltage up a little bit. I'm going to raise the voltage up a little bit. So if you want to reach 5 meters per second, you need to supply 6 volts to this motor. That's what feed forward does. And then the controller will put 6 volts into the motor. And and you're expecting it to reach 5 meters per second, but it doesn't. It only reaches 4.5. That's what feedback is. Feedback says, hey, my goal is 5 meters per second, but I'm only at 4.5. So feedback tells the controller to raise the voltage even higher because the motor is not reaching its goal. Yep.
So if we were doing feed forward control on, say, the robot, we would probably take measurements. If I give it 3 volts and it goes this fast, and I give it 5 volts and it goes this fast, and you'd wind up with a little table,
Yes.
right?
Yeah.
And then when you said go 5, we'd go look in the table and say, well, that takes 2 volts,
Pretty much.
right?
Yeah.
But that's only good. And that would work if the table was completely accurate, right? But every time you mess with the robot, the table gets wronger and wronger and wronger.
Absolutely. That's absolutely right. You might have heard that we do something called characterizing the robot.
We have the SysID program,
Right.
which runs tests with the motors to try and figure out what good feed forward looks like. It's a little iffy, but
Yes.
it does an okay job.
It does an okay job. As I said, feed forward, the constants need to know a little bit about your robot. And the only way to determine feed forward constants is through empirical, which means real life testing. That's what the SysID program is for. It is used to what we call characterize the robot. Characterize meaning get some constants out of it, run some tests on it. And what sysid does is it runs a series of tests of like testing out how the motor turns and how it resists how it resists acceleration and whatnot. And then from those sysid tests, we get feedback constants that plugging them into some mathematical equation will basically tell us a little information about the robot, and that goes into the prediction algorithm. Okay, yeah. Feed forward here. Feed forward, a very important thing to note is that feed forward only works with velocity. It does not work with position output. You cannot ask feed forward to go from 0 meters to 10 meters. That's a position, that's a distance. You need to do it you need to work with it in velocities, telling it to go from 1 meter per second to 5 meters per second. Because what feed forward is really good at is it predicts the voltage that you need to get to some speed, and only some speed, okay? And again, as I said, and what Carson talked about, sysid, it uses empirical data, only acquired from testing, where you then can predict you can predict the ways that the motor behaves. For example, static friction. Static friction means going from 0, how much voltage do you need to get the motor to start moving? And this, of course, differs. If your motor has nothing on it, it will take very little voltage for it to start moving. If you have a massive arm attached to it, it will take more voltage to get it to start moving. That's why these feed-forward constants need empirical data. You need to test it in order to get these constants. For example, another example is gravity. Gravity plays a big part in an arm where the force differs, the voltage differs based on what angle your arm is at. Or elevator, the higher your elevator, the more force you need to keep it up to compensate for gravity. And again, feed forward is a prediction algorithm, but feed forward's job is not to correct for error. That is feedback's job, and that's the next slide. Does anyone have any questions about feed forward? That was feedback was not the next slide. This is feed forward. This is the magic equation. To break this down, you might need to know, no calculus, never mind. So to walk through this, V equals Ks times sine D plus Kv times D plus Ka times derivative of D. Basically, the V stands for the voltage. Remember that feed forward is an algorithm that you plug in a velocity that you want to reach, and it will output a voltage. That's the voltage that it outputs, the voltage for feed forward. I said that one of the things that feed forward measures is static friction, how much voltage it needs how much voltage it takes for the motor to start moving. That's this part right here, Ks times sine D. Ks, K denotes a constant. It's just a number. It doesn't have any units, it's just a number. And these constants are what are very important and can be determined through empirical testing. So Ks is your static friction constant, and times sine of D is denoting the direction of the motor that's moving, either positive or negative. Kv times D is the cruise at velocity, and I'm pretty sure, let's see, I included explanations here. So if you let a motor start spinning and then you suddenly let go, it will slow down, right? That's just natural. Kv is the cruise velocity, and that's saying, okay, you got the motor to now turn at 5 meters per second. How much voltage does it take to maintain that velocity? That is what Kv is. And
is that absent a load, or?
Say again?
What about the load? Is that without the load?
No, that's with the load. That's whatever.
However much it slows down.
So that's the amount to keep moving, whatever the situation is.
Yeah, whatever the situation is, basically. Or sorry, like in the moment that you're testing it, Yeah, if you test, like, say, an arm, if you test an arm and get this kV constant without some kind of load like a cube or something, it will not measure for that cube. No. So feed forward and stuff has its pitfalls. Feed forward cannot predict a cube. It cannot predict, like, something else. If you want it to,
So you'd have to take those measurements in the exact situation you
Exactly.
expect to be in,
right,
or
and
they're wrong.
right, exactly. And to be fair, if feed forward is wrong, which most of the time it is, it can never get it perfect. That's what feedback is for. It corrects for that error. And if you have a good feedback algorithm, then your system should be fine, right? KV is for, cruise velocity, and you multiply it by the velocity. And then KA here is how much voltage you need to make it accelerate, to basically have a motor at 5 meters per second. How much extra voltage do you need to supply to make it move just a little bit faster? And that's derivative of d, which is the acceleration. And this equation changes when gravity is included. Gravity does something like plus kg, which is the gravity constant, times cosine of theta, theta being the angle that your arm or subsystem, whatever, is at, and that's that's just part of the equation to compensate for gravity. Here's a link right here. These slides are in the FRC 2023 drive folder. This link right here tells you all about these feed-forward constants. Any questions about feed-forward?
So again, in case of the robot, none of us are ever gonna know any of these numbers or anything like that. We're gonna characterize the thing and that's it. So
Yep.
something like this is sitting inside, but we're not ever, none of us are trying to calculate KV or anything like that, right?
It's all
Based on
computer
physics or
based,
anything, yeah.
essentially. We get the algorithm to figure it out and then hope that it did an okay job. And you can fudge with them a little bit, but
Yep.
it's hard to like figure out whether it's actually doing what it's supposed to.
Right.
Especially like if you make a giant change, you'll notice, but if you're trying to do fine tuning, it's actually quite difficult.
Mhm.
With like, especially if you're doing it with the feedback, because the feedback will smooth out any problems essentially with the feed forward.
Yeah.
So.
WPI libs, like the Java library that we use, WPI libs feed forward is a little bit of a black box. sysid is a little bit of a black box. You make it run some tests, it will spit out some numbers, but you don't really know what's happening inside. That is how it is, and yeah.
But I assume when you characterize something like that, if you did the robot without the carpet, you get one set of K values. If you
Yes.
do it with the carpet, it is a different set. Or
Yep.
if you replace a motor, it'd be,
Yep.
you have to recal, each of those events probably causes recalculation.
Absolutely, yeah, because something about your robot changed, so you recharacterize to get the behavior, the new behavior of the robot.
And that's the big downside of feed forward, right? It's at best, it's just a single point in the operating space. And
Yep.
Exactly, and if you change anything about the robot, like physically, if you add any weight or you do anything,
Yep.
it immediately has an effect on how good the values actually are.
Absolutely. All right, feedback. This is the other part of it. This is the correction part of control systems. Feedback is unlike feed forward. A feed forward can only work with velocities and speeds. Feedback can work with position or velocity. This is the guy that corrects for error. This is the guy that tells you what you're doing wrong and what you should do to correct it. So this PID stuff compensates for, number one, inaccuracies in feed forward. If your constants are a little bit off, your feed forward voltage will be a little bit off, your motor output will be a little bit off, and feedback will correct for it. Number two, real life physics. Things don't always go perfectly. Feedback will try to correct for the error, again, the difference of where you're supposed to be and where you're actually at. And the big part of PID is a PID controller. This controller takes an input and will spit out an output. This input is the error, again, where you want to be, and the difference of where you want to be and where you actually are. So the input to the PID controller is error, The output is the voltage to correct for error. And this voltage can be positive or negative. If your motor is undershooting, the PID controller will see that the error is positive because say you want to be at 5 meters per second and you're only at 4.5, your error is positive 0.5 meters per second. Your voltage will be positive because you want to add more power, more voltage into the motor. And if your motor is overshooting, you want to be at 5 meters per second, but you're actually at 6 meters per second. Your error is -1, and thus your voltage will be negative because you want to decrease the voltage a little bit. Anyone have any questions on this? Good.
Oh, so it's not actually technically negative voltage. It's like you're subtracting from the positive voltage
We'll
you
get to
already
that.
have.
Yes, yes. That is a very good clarification. There's no such thing as negative voltage. Feed forward and feed back, if you saw the closed loop diagram, they work together, and thus the voltages, we'll see how they come together, okay? Let's dive into PID a little bit. This will go into a little bit of calculus. I'll try to simplify it as much as possible. PID is an algorithm, a correction algorithm that stands for proportional, integral, and derivative. Big scary words, okay? And big scary formulas right here. You can see the whole PID algorithm essentially takes in the error. The error is on this left side of the flow chart. It inserts the error into the PI and D parts of the algorithm and then sums all the output.
So
Okay.
EFT here is your error signal?
Say again?
EFT
is
is
error, correct. Okay. Proportional. Proportion. What does the word proportion mean? It's a ratio. Proportion is a linear relationship between two things. For example, you've heard the proportion like 2 to 1. 2 to 1 means if you have 2 parts of one thing, you have 1 part of another thing. It's a relationship. So if you have a proportion of 2 to 1, if you have 4 parts of one thing, then you have 2 parts of the other thing, right? The idea of proportion is that you are relating together in a proportion the error and the voltage. You're basically what proportion is saying is if you have more error, then you need more power to correct for this egregious error. If you have less error, as in you're close to your set point, then you should supply less power to correct it. Okay, so say my set point is to be where Carson is. Okay, but I am actually right here in this point in time. This is a very large error, and thus the proportional part of the PID controller will say you need to supply a lot of force to get to where Carson is. Now, if I was closer to Carson, my error is less, and thus the power output is less. Now, proportional. Now, this type of control, this P controller, P standing for proportional, is kind of the heavy lifting of the PID controller. This P controller is what corrects for the majority of the error that you have from the feedback output. And in some circumstances, just a P controller is good enough. So in this graph right here, you can see what just a P controller can do. If you start at 0 and your goal here is roughly like 0.95 right here, this is your set point. You start off at 0 and notice that you shoot up really, really fast. That is because at the beginning points in time, you are really far from your set point. Your error is large. Thus, because of this proportional controller, your error is large, your output is large, your motor output, your voltage. So thus, the motor spins up really fast. All right. We're heading back to feedback. Okay, feedback is PID again. There are 2 types of PID controllers. And at this point, I'm going to start talking about some more in-depth concepts. And so do your best to follow along, and please raise your hand if you have any questions. This section is less so of general knowledge and more so of explanations so that future people who watch this video can understand, especially the future programmers, right? Okay. So PID controller is like the normal PID controller. It sees what a PID controller does is it takes in an error and it corrects for that error by supplying a voltage. That process is effectively immediate. It is fast. It's incredibly responsive. You see, like immediately when you input an error, it spits out super fast an output voltage of how to correct for that error. That's why I call it sharp correction. So, your motor is spinning at 5 meters per second, and then suddenly, for whatever reason, maybe some resistance comes in, suddenly it drops to 2 meters per second. The PID controller will kick in really fast and see that the error is now 3 meters per second, and then immediately supplies more voltage to correct for that sudden drop in velocity. Okay, so that's why I call it aggressive correction. It jumps right to the bat, right? It sees that error that dropped to 2 meters per second and is like, hey, amp it up a bit right now. Okay. Now this contrasts from a profiled PID controller. This is the kind of the opposite of a normal PID controller. This corrects it in a smooth manner. It sees an error, but it doesn't immediately act on it. It makes a plan to fix it in a smooth way. So, like the motor is spinning at 5 meters per second, and then suddenly it drops to 2 meters per second. Same scenario. What profile PID controller will do is it sees, hey, okay, the error is 3 meters per second. I'm gonna take my time and I'm just gonna relax. I'm gonna ramp it up just a little bit. I'm gonna be like, hey, can you go a little faster, please? And it'll get there eventually. It'll get back up to 5 meters per second, but it's not like, hey, like more voltage right now. It's just a little more relaxed, smooth. That's what profile PID controller does. It makes a plan saying, hey, within 2 seconds, let's ramp back up to around 3.5 meters per second. You don't have to get there right now, just over a little bit more time. You'll get there eventually, but let's set some goals, right? At 2 seconds, reach 3.5 meters per second. At 3 seconds, reach 4 meters per second. And at 4 seconds, you should be at 5 meters per second. That's the plan, okay? And that's good for smooth correction. Take, for example, an elevator. If your elevator, you're at 10 meters, 10 meters way too high, 2 meters, okay? Say you're at 2 meters and suddenly you set the set point to 0 meters. You don't want the elevator to just come crashing down, right? To get to it as fast as possible. You want it to go in a smooth manner. That's what profile PID controller is for. It will make a plan for you to get from 2 meters to 0 meters, and it will do so in a smooth fashion. It will make a plan saying, hey, I'll give you 2 seconds to reach 1 meter, and then another 2 seconds to reach 0 meters. And thus, to go from 2 meters to 0 meters will take 4 seconds with that plan, okay? That plan that I'm talking about is called a trapezoidal motion profile. That profile part is why it's called a profile PID controller, okay? Now, a distinction, WPI-lib, the Java library provided by WPI, that's like the main FRC library. They call it a profiled PID controller. However, different libraries call it different things. You might have heard of CTRE's Motion Magic. That is the equivalent of profiled PID controller. Rev also has a Smart Motion, part of their library. It's a feature called Smart Motion, which is also a profile PID controller. However, it's pretty bad according to people who have actually used it. So don't use that. Just use profile PID controller. Okay. And so because normal PID controllers are very aggressive in their correction, very immediate, it is really good for velocity correction. For example, a flywheel, right? If a flywheel, you're spinning at a really high speed and you just shot a ball and that, resistance slows down your flywheel, you want to ramp back up really fast. That's what a normal PID controller is really good for. But an elevator, again, you don't want to come crashing down or shooting up super fast to your set point. You want to make a smooth transition. And that's what a profile PID controller is for. That's why this is recommended. The profile PID controller is recommended for position correction. Okay. And you can see right here, this is the graph of a profile PID controller. Let me deconstruct these little lines for you. The blue dashed line is your set point. Your set point is, you're going from 0, whatever the units are, 0 to 1,000, okay? The black part of this graph is, notice, it's a trapezoid. That's why they call it a trapezoidal motion profile, because this black part is your velocity. It, again, this whole trapezoid stuff is a plan. This trapezoid that it generates is the plan, the velocity plan of, hey, how fast are we going to ramp up, and what speed are we going to reach in order to get from where we are now, 0, to our set point, 1,000. So what this trapezoid is basically saying is increase the velocity from this time from 0 to 150 milliseconds, right? From 0 to 150 milliseconds, let's increase the velocity. So let's make the elevator, say, start going up, start accelerating upwards. From 150 milliseconds to 450 milliseconds, keep the velocity constant, okay? Keep the velocity constant. So at some point between 150 and 450 milliseconds, the elevator will be going up at a constant velocity, a constant rate. And then once it's close to its set point, it will decrease the velocity, saying, slow down, right? Because you got close to your set, you're getting close to your set point. So, slow down so that you don't overshoot. Now, the red line here, you can probably guess it's acceleration. That makes sense because that makes sense because from at this point, you are increasing your velocity, thus your acceleration is positive. And down here, when you're slowing your velocity down, you are decreasing your acceleration, thus is negative. Or decreasing your velocity, thus the acceleration is negative. And then the blue line, the solid blue line, is your position. Okay, your position, say your elevator going from 0 to 1,000, whatever. Notice here, and notice at the beginning, it's a little bit curved because your velocity is increasing. So, and at the middle here, it's continuously at a very steady pace, rising up to its set point, and near the end, it will smooth out, it will curve, slow down near its set point. That's what a trapezoidal motion profile does. Does anyone have any questions about this?
So the black line, the velocity, what the profile controllers are is add a velocity limit, never go faster than this, which makes sense in an elevator. You if you got a powerful elevator, you still don't want to go 100 miles an hour right now. And then the red line is doing the same thing for acceleration, right? Never accelerate harder than this, otherwise you'll be crushing people. Right?
Absolutely.
So the profile controller is adding those two constraints on top of everything else you just showed us.
Absolutely. So that's a great point because you need to define somewhere with this profile PID controller, with the plan that it makes, you can't just with the plan that profile PID controllers make, you have to give it some constraints, otherwise it could generate some crazy plan. You have to tell it, hey, like my elevator, Like I don't want it to go that fast. I want to limit the acceleration to 2 meters per second. And it doesn't accelerate that fast either, so I want to limit it to 1 meters per second squared. Those are two other constraints, two other variables that you have to supply to the profile PID controller.
So we would pick those two for the robot, because we don't wanna twist it any harder than this or move something any faster than that.
Exactly. Actually, I think I jumped ahead a little bit. This slide explains the trapezoidal motion profile. Again, profile's plan. The downside, right, you need to specify the maximum velocity and the maximum acceleration of your plan, your motion profile. Yeah, this part explains it really well. Let's see, the velocity here, you know, you're accelerating, the velocity's increasing, it's steady, and then it goes down. That's the trapezoid part. Your acceleration is positive at the beginning because you're increasing your velocity, negative here, and your motion, you can see the 3 different phases of a trapezoidal motion profile. This is your position. Up here, in the beginning, it's the acceleration, speeding up. In the middle is the constant speed, and at the end is deceleration. So this diagram I found really helpful. You guys can definitely check that. All right. So I'm gonna go over some examples of different subsystems of our robot, because all of this, you know, theory talk, it's a little bit hard to see why or how it applies to different subsystems. I'm gonna go over a bunch of subsystems and tell you, you know, like how we control it. Okay. So again, with these control systems, you got feed forward, the prediction algorithm, and feed back, the correction algorithm. Let's take an elevator that we've been talking about for a while. The elevator, the feed forward part, you got some some constants that you'll need are the standard feed forward constants, your static friction, your cruising velocity, and the resistance to acceleration constants. Plus, you need something to correct for. You need something to predict the effect of gravity on your elevator, and that's what kg is. Now, there is a specific class in WPI-lib, and if you don't know Java, ignore what I'm saying. There's a specific class in WPI-lib called elevator feed forward, where you plug in KS, KV, K, and KG, and it will output you that voltage. So it's kind of pre-built already for you. And feedback is the correction. Feedback is the correction, and remember that profile PID controllers work best with position, because to get from one position to another, you want a smooth plan to get from position A to position B, like an elevator. So because elevators measure position, or works with position, that's like your main, that's your main definer. You want to use a profile PID controller, and it works better. A profile PID controller works better anyway, because then you get that smooth elevator motion. Anyone have any questions about an elevator? Okay. Swerve drive motor. This is the, remember, swerve drive module has 2 parts, the drive motor and the turn motor. This is the drive motor, which is just movement and velocity. This is the drive motor saying turn, start driving at 2 meters per second. Your feed forward, the prediction algorithm will have some standard feed forward constants, Ks, Kv, and Ka. Anything that just has like a standard set of constants, of feed forward constants, will use the simple motor feed forward WPI class. Feedback, how do you correct for velocity error? Well, you're gonna need some aggressive correction to correct for any overshoot or undershoot in velocity. So because you are working with velocities for the drive motor, you want to use a normal PID controller, because that's what it's best at. On the other hand, the turn motors work. Turn motors, you don't say turn at 5 meters per second. You say turn to 45 degrees, and degrees is a position, right? for feed forward, again, it's the same thing. You're not compensating for gravity, so KSV, KV, and KA are your standard feed forward constants. Simple motor feed forward, same thing as the drive motor. Your feed back, you want to get to certain positions, like turn to 59 degrees exactly, and thus you want to use a profiled PID controller. Now, here's the thing, and I don't know if I have no, I don't have like an explanation for this. In the code, we did not use a profiled PID controller. The reason why is because, like in theory, because we're working with position, a profiled PID controller would be better. There are some exceptions to this rule. Remember, like a profiled PID controller is used for smooth correction, a plan from getting from point A to point B. A normal PID controller is good for aggressive correction. Getting there, right now. The issue is that swerve drives need to react really fast. An elevator doesn't need to get from point A to point B in half a second or even a quarter of a second, but a swerve drive does, right? You tell it to, start going a certain direction. You can't wait for the turn motors to finish its long plan. So that's why instead we use a normal PID controller. One, because it eliminates the need to tune two more constants. Remember, you need to specify a max velocity and acceleration for that motion profile. And number two, it works better because you get that aggressive correction from normal PID. Any questions?
So you're saying you didn't need to constrain how hard or how fast those turn wheels turned.
Pretty much.
So you could leave that guy. You didn't need those constraints.
Yeah.
So you were driving him as fast as your controller could do it.
Pretty much. Yeah, because swerve drive's all about speed. It's kind of just what's more applicable to your use case. I did have that explanation of position equals profile PID controller, velocity equals normal PID controller, because those are some good rules to follow, but of course it depends on your use case. An arm, as you were talking about, an arm needs to have the standard feed forward constants, Ks, Kv, and Ka. It also needs to compensate for gravity, but in a special way. Unlike the elevator, which goes up and down in a vertical axis, an arm can rotate, and the prediction algorithm needs to know what angle the arm is at or wants to go to in order to predict the effect of gravity on that arm and thus compensate for it. So thus, kg times cosine of theta, gravity with an arm angle. And this calculation stuff, again, is pre-built into WPI Lit. It's called arm feed forward. That's the class that you would use. And again, the arm here, you're not saying, arm rotate to 5 meters per second. You're saying rotate to 90 degrees. You're working with positions here. Degrees is positions, and thus using a profiled PID controller would be the best. And going back to what you were saying, on the arm, we used a profiled PID controller with that smooth motion profile because you don't want it to aggressively correct from 0 to 90 or something like that.
We put a mechanical stop in as well.
Yes.
Did it go like almost all the way up?
Yeah, so the profiled guy constrains acceleration and velocity, and it's up to you to constrain position. All of them have to be constrained to you.
But in some of these systems, you don't know what's going to happen, so you have to be careful.
Exactly. Yes, mechanical. See, once feedback corrects for feed forward, but what corrects for feedback is mechanical. Anyways, flywheels, another example. You want to maintain a certain velocity. You deal with velocities here, spit out to a certain RPM. Your feed forward is going to have the normal feed forward constants. That's simple motor feed forward class. And again, you want to work with velocities, so you use a PID controller as described in earlier slides. And to finalize, there are no hard and steadfast rules to PID. Okay. I talked about how feed forward and feedback work together, but sometimes, you don't even need feed forward. Just feedback can be okay. And how that will work is that, remember, feed forward is the prediction algorithm. It gets you the majority of the way there because you're predicting based on the constraints and knowledge of your system how much voltage you need to get to that point. So if you take that out of the equation, you're just going to have feedback that's working on error. Remember, feedback takes in the error and outputs a voltage. And since you have no feed forward that is like moving the system, predicting the output, the feedback is just going to have a lot more error to work with. And it can still get you there. It's just going to do it in a little bit of a different fashion. And again, not all PID is necessary. Not all parts of PIND are necessary. Oftentimes, this could actually work against you. For example, the gyro auto balance that Carson came up with, shout out to Carson, good morning, is just a P controller. There's no integral correcting for steady state error. There's no derivative correcting for sharp, sharp changes in the angle. The gyro auto balance is just a P controller. More angle tilted, more force, more movement upward.
And that was possible because the mass of the balance beam was much heavier than the mass of your robot.
Yeah.
And that's why you could do just a low
Well,
T and
it's only the mass, like pulling off it really counts. So since it's only at like a 15-degree angle, didn't have too much of an effect of like real gravity on the friction. You're able to get away with having a smaller thing, save the balance with how heavy the ring ends up being. So yeah.
And the swerve motor turning does not have an I, does not have an integral part. It's just proportional and derivative. Proportional to correct for the majority of the error, more error, more output, but the derivative to fight against the proportional to smooth out the curve to not to prevent overshoot. Because if you have overshoot on your turn motors will start it will get to the set point, but overshoot it and then come back and then it will jitter. And so last year's robot, if you heard the turn wheels, you turn it on and it goes like, that's because it's overshooting. That's because the constants were not properly tuned. Also in part because it was using the profile PID controller, which causes, introduces more constraints, more problems. But in essence, the constants were too large, and thus the turn motor was overshooting. Again, sometimes profile PID controller is too complicated. You have to introduce two more tuning variables, the max velocity and acceleration, for the trapezoidal motion profile. Yeah, we tried to use it for the swerve turn motor, but too complicated. And most teams, I talked to a bunch of teams at COM, and most teams just do a simple proportional loop on their as feedback on their turn motors. That's it.
Which is BS.
Now, why didn't that work for us? Variety of reasons. And remember, all of this is theory, and nothing in real life works in theory. So, I hope you got something. I hope you got something from this set of slides and understood a little bit more about how control systems work.
I was going to ask you one thing before you go on. Could you explain how you get the error in the various systems that you were talking about? You showed a couple of those different systems, and I'm curious kind of what was the error in
What was the
system?
error? I'll go through each of them really quick. The error for elevator, your set point is 2 meters high, but your elevator is only at 1 meter. Thus your error is 1 meter.
But I guess in the case of the elevator, did you have a sensor that detected that, or was it calibrated from the?
How do you get there?
Yeah.
How do you get there? Yeah, motor encoder output specifically. The Falcon 500s have an integrated encoder keeping track of the position and velocity. But for an elevator, you only care about the position. It has its own units and Falcon units, and you do a little bit of math, translate that into meters based on the gear ratios, chain links, whatever.
So you're applying a voltage and then the motor is returning an encoder value after that. You take that encoder value, put it in your algorithm and adjust the voltage again.
Exactly.
But your question's really good, is for feedback, you always have to have telemetry, you have to have some kind of encoder or some
Yes.
measurement, it adds that complexity to your system.
Yes.
You have to have it.
Absolutely. Again, a controller is basically a set of eyes on your motor, on your output, your plant. And that those, in reality, those set of eyes are like an encoder, something keeping track of where your motor is, what your motor is doing. Yeah. So it turns out that's not the end of my slides, because I actually have some code examples, courtesy of Carson's suggestion. So if you don't know Java, you can now zone out. However, you can see we have some instance fields up here, like a swerve drive motor, a drive motor here. Does not need to compensate for gravity. The class is simple motor feed forward, and your PID controller is the normal PID controller, as denoted right here, because you want to do aggressive correction for velocity. We're setting the constants here. We're initializing these variables with the constants that we pass in KS, KV, and KA for feed forward, PI and D for PID controller. And this code right here is like the where everything comes together. First, you define your drive voltage. This is not the final output, but you first define the drive voltage variable. You take the feed forward algorithm, the prediction algorithm, and calculate. You give it your goal, your speed in meters per second, and now this feed forward will now predict for you how much voltage you need to get to this set point speed in meters per second. But again, where's but then the error part, the correction part comes right here. The PID algorithm is your correction algorithm. You plug in the error, which you don't calculate the error. You just give it, number one, the measurement of where you actually are right now, and this we have a helper method of getting the drive wheel velocity in meters per second, and then you specify the goal where you actually are in the goal where you want to be in speeds meters per second. You give it the measurement and the goal. The PID will calculate the error and plug in into the PID equation and spit out a voltage that you add onto this variable. And all you do is drive motor.set voltage, because remember the output is feed forward plus feedback voltage is equal to your final voltage.
That get P, get I, and get D, those are just returning constants you built into your code, or
numbers.
the result of the characterization algorithm or something like that.
It's like set in a file. It's all this concept. You just feed it in.
What's the sampling rate for something like this, or what's the?
It runs at the same rate as the robot, I believe. It's 20 milliseconds per cycle.
So you're retrieving and recalculating on a 20 millisecond interval.
Yeah.
I assume the physical system, if you were to calculate the damping constants and stuff, would be much longer than that. So 20 milliseconds must be plenty for the system to work with.
An ARM. I included an ARM because ARM, it works with position and thus works with a profile PID controller. You can see how it will instantiate the code here. You got your ARM feed forward because it has to compensate for gravity with the ARM angle taken into account. And you're working with position, so your feedback will be a profile PID controller. You get KS, KG, KG is your special one now with the gravity. KS, KG, KV, and KA, your profile PID controller gets PID, that's normal stuff, but then the trapezoidal profile dot constraints, now those are the constraints for a trapezoidal motion profile. You specify the max velocity and max acceleration. And basically the same thing, okay, no, not the same thing, sorry. With profile PID controller, with profile PID controller, rephrasing. Feed forward, again, works with velocities only. But the issue is that we should be working with positions here. We're working with degrees, and that's a position. So how do we get from position to velocity. Because we need a supply of velocity for feed forward. That's where the motion profile comes in really handy, because your motion profile will get you from position A to position B, but that plan also includes a velocity graph. You saw like the trapezoid part of the plan and acceleration and whatnot. That velocity part is really important because we can take that velocity, aka at a specific point in time, based on the plan, how fast should we be going, based on the motion profile plan. And then we plug that into feed forward, because feed forward works with velocities only, okay? So first, we update the motion profile based on where we are now. We call feedback first, feedback being the profile PID controller. We give it the measurement and the goal, aka where we are right now, the angle, and the set point of your angle, okay? That's in like radians or something, and it will output a voltage. But when you call calculate here, it will update internally the next velocity set point that you want to get to. You know, it will that trapezoid. It will then internally set the next velocity that you want to reach, and you can access that next velocity goal by doing the get set point method. Set point being like where you want to reach, dot velocity, and now this profile PID controller, you know, returns you that velocity part of the motion profile graph, which you can plug it into feed forward, because feed forward works with velocities only. This arm feed forward specifically takes in the angle of the arm, because it needs to plug it into the cosine theta part of feed forward, and it also takes in the velocity set point that you want to reach, and then you set the voltages. Yeah.
So the profiles, the arm feedback is inside arm FF, so the profile's inside there.
Sorry, what profile?
I'm looking at on the right-hand side.
Yes.
It's arm feedback, that's the profile PID.
Correct.
That's inside arm FF, which is the general.
It is not inside. Do you mean inside as in
I'm looking at you have it as a variable inside the calculate, right? It's passing.
This arm feedback?
Yes.
Oh, this arm feedback is just referring to the instance field up here. This is all one class. So you're just referring to the so like inside the feed forward calculate parameters, you are just referring to the feedback
Right.
Instance field, and you're grabbing the velocity really quick from the profile, from the motion profile.
Right. Okay.
Yep. And that is all I have for my slides. Any final questions?